All right, good morning. Good Sunday morning, actually. So looking at logarithms, okay, common logarithm, which is a logarithm of base 10, and a natural logarithm, which is logarithm of base e. So everything I'm going to show you, the concepts, the properties apply to both of them, whether it's a common log or a base e, or if it's any other base, base 2, base 3. Then I'm going to show you some examples and then show you the parent function for the logarithm that goes to it. And just like that, you have different properties. Okay. So first thing is common logarithm, written as just log without a base number, 10. That's what your calculator is working. Okay. So the rule is, first of all, basic property. Log base 1 is equal to 0 automatically, because basically what it says is that anything to the 0 power is equal to 1, and that's where it comes from. Then you have something where you have log base base. In other words, this is the same base, and that's automatically equal to 1. You have something called product property. Product property basically means that if you have the log of an m times n, you can rewrite it as log base of m plus log base of n. Quotient property, basically if you have division, log base of m divided by n, that's the same as log base of n minus log base of n. Power property, log base of n to the n power rewrites as n times log base b to the m. I'm sorry, log base b of m. It's a tongue twister for me. And then change of base formula, which I think we've seen before, where you have log base b of a is the same as log of a over log of b. Okay. So you'll need to know forwards and backwards. So if you're giving it in this form, to be able to write it in quotient. If you're giving it in this form, to rewrite it in a subtraction format. Okay. So basic examples of this one right here, if you have log base 6 of 1 is equal to 0, or if you have log base 4 of 4 is equal to 1, that's for your basic properties. Product property, again, this is the same as if you have log base 3 of 8 plus log base 3 of 3x, it's the same as log base 3 of 8 times 3, which is 24. Expansion, this is where you have to, and I'm going to use the word factors here because that's actually what it is. Okay, you might have to factor. So this trinomial becomes these two factors, and then you can rewrite it as two natural logs. Okay. And by the way, again, notice that this is a natural log, this is log. The rules apply regardless of what you're using. Condension, again, log 80 minus log 16 becomes log of 80 divided by 16, which is log of 5. Expansion, again, becomes log of x, log base 2 of x minus log base 2 of 5. Condension, rewrite this as natural log of 9 to the third power because this goes to the exponent. Expansion, rewrite this as 2x times log base 7 of 3. And again, I'm going to go through examples. I'm just kind of just showing you what you're going to be looking at. Then evaluation, you have log of 138 over log of 5. This is called change of base again. And again, this is for calculator purposes as well. Okay. All right. So let's look at some examples now. Okay. Product property. First of all, condension and expansion. So the condension basically says I want to take, since this is addition, I'm going to multiply. So I rewrite this as log base 3 of 9 times 5, which becomes log base 3 of 45. That's condension. Again, condension product, so log 6 of x minus 3, so log of 6x minus 18. Again, addition, so rewrite it as multiplication, so the natural log of 4x squared times 3x to the cube becomes natural log of 12x to the fifth power. Expansion. Again, 72, and we want to expand it. Now, there's different possibilities on this. The ones I'm going to give you are probably the most common ones, hopefully. But basically, this is the same thing as log of 8 times 9. Okay, that's one possibility, by the way. So I would write this as log of 8 plus log of 9. Okay. Here, I can write this as a natural log of 3 over 2 times 3 over 5. That way, 3 times 3 is 9, and 2 times 5 is 10. So then I would write this as the natural log of 3 over 2 plus the natural log of 3 over 5. That's what expansion does. This one right here, this is called difference of squares. That means that this is going to be x plus 2 and x minus 2. So I can rewrite this as log base 5 of x plus 2 plus log base 5 of x minus 2. And that's product property. Quotient property. Okay. Subtraction means turn it into a division problem. So natural log of 96 divided by 6, which becomes a natural log of 16. Okay. Log of 8 to the x to the 10th power divided by 4x squared. So that becomes log of 2x to the 8th power. And again, division means you subtract exponents. Ooh, this one's going to be interesting. Log base 7 of square root of 40 over square root of 5, which becomes the log base 7 to the square root of 8, because 40 divided by 5 is 8. I can reduce this, actually, to log base 7 of 2 root 2. And the reason why is because this 8 becomes the square root of 4 times 2, which is where the 2 root 2 comes from. Okay. Expansion. Again, something that divides into 8. I could go log base 3 of 24 divided by 3. So it becomes log base 3 of 24 minus log 3 log 3 of 3. Okay. Division. So natural log of 3 minus natural log of 4. Still division. Log of x minus 7 minus log of x plus 1. That's expansion. Power property. That basically means I'm going to rewrite this using my coefficient as an exponent. So log of 6 to the 3rd power, which I can do this as log of 216. Again, move it to the exponent. Log base 4 of 81 to the 1/2 power. So log base 4 of 9. Again, coefficient to the exponent. Natural log of 4 to the x minus 1 power. Okay. Expansion, again, power to the coefficient. So x log 2 of 5. Now, this one right here, I'm going to rewrite this. This is a natural log of 2x plus 1 to the 1/3 power. Okay, that's what cube root means, is 1/3 power. So 1/3 natural log of 2x plus 1. This is the same as log 6 of 8 to the negative 2. And the reason why is because 8 squared is 64. in the fraction form and it's negative. So negative 2 log 6 of 8 is what I'm looking for. Okay? And that's power property. Okay, what's my next one? All right. So condensing logarithms using all properties together. I'm going to go through all of these. I'm going to show you a few. Okay. So here's what I do have. I have two coefficients, which means powers. Okay, so I'm going to go and do those together so you can kind of see them. So you end up with log, I don't know why I keep writing LG instead of LOG. 4 of 9 squared plus log 4 of 2 cubed. Addition means multiplication. So log 4 of 9 squared times 2 cubed, which again, if I finish this off, would become log base 4 of 648. 648 comes if I do 9 squared times 2 cubed. So 81 times 8. Okay? And that's what you look for in condition and subtraction. Let's see, what else do I have here that I want to do? Again, coefficient to power. Coefficient to power. It's also addition, so it means I'm going to be multiplying. So I'm going to skip one step here and go natural log of PQ to the third power times PQ squared to the fourth power. Okay, so addition became multiplication, coefficients became powers. Then I'm going to go ahead and distribute. So it becomes a natural log of P cubed Q cubed times P to the fourth Q to the eighth. And then anytime you multiply, you add exponents. So it's going to become the natural log of P to the seventh Q to the 11th. Okay. Let me see. Here's an interesting one. Number 25. So it's subtraction, which means I'm going to turn this into division. This is a coefficient to the power, and I have an addition right here. So I'm going to rewrite this and do what I can right now. Okay, so watch. So I have log of 72. I'm not going to do the subtraction yet, but I'm going to go ahead and, oh, there's a 2 right there in front as well. I'm going to fix this right side first. So this will go here. Okay, so here's what I'm going to do. Log, parentheses, log 4 squared times 32 to the 1/3 power, kind of like that. So what's 16 times 32? I can do that. 16 times 32 is 512. So this is going to become 512 in here. Wait, what did I write 2 logs? I don't know why I wrote 2 logs for. Hold on. There's only supposed to be 1 log. That's my fault. This doesn't need to be here. Yeah, that's what I want. Okay. Then I'm going to rewrite this for division. So log of 72 divided by, this becomes 512. 512 to the 1/3 power, kind of like that. And that will give me the log of 72 over, what is 512 to the 1/3 power? 8. So this becomes log of 9. Just like that. Okay, that's condension. In expansion, I always think expansion is a little bit easier, truthfully. I want to basically rewrite this with addition, subtraction, and coefficients instead. So this is multiply, so I'm going to rewrite this first as log base 7 of x plus log base 7 of y cubed. And then because of this, I'm going to move this to the front, so it becomes log base 7 of x plus 3 log base 7 of y. Kind of like that. Okay. First thing I'm going to do in this one is I'm going to rewrite this as log of a cubed b to the 1/2 power. Square root is the same as 1/2 power. Then I'm going to do, since this is an exponent to a coefficient, so 1/2 log of a cubed plus, do I want to do it this way? Hold on. Make sure I want to do it this way. Log b, and the reason why I put it in parentheses because the original was, they're both square root. Then I'm going to rewrite this by moving this in front, and I'm actually going to distribute this through, so this is what it's supposed to look like now. So this becomes 3/2 log of a plus 1/2 log b. Okay. And that's what expansion looks like. Takes a little bit of time to get used to the properties, but that's what we're looking at. Okay, so logarithms, the parent function itself. Okay, so that's part of the properties. The other properties are the domain, range, and items of that nature. Okay. So logarithm, first of all, base parent function, I've written this before a couple of times already, is f of x is equal to log of base b of a. Okay. And this looks like a graph that kind of looks like this. And then the exponential one, which we've kind of already covered, looks more like this. Okay. The difference is this. This has a vertical asymptote, kind of like this. This one has a horizontal asymptote, like this. Okay. And this one right here is actually at x equals 0. This one right here is at y equals 0. Kind of like that. Okay. So the log, I know it says to use inverse exponential function to graph this, but here's what I'm going to tell you, especially with an updated version of the calculator. You can graph a logarithm using the function alpha window. Number 5 is your log base. So if I want to graph log base 3 of x, that's what I'm going to put. And you graph log base 3 of x. Okay. Let me pause this. All right, so what that means is I can graph a vertical asymptote right here at 0. Okay. I have an x-intercept at 1, 0. Let me make sure that's true. Yeah, right here, 1, 0. And then my graph is going to go kind of like this. And again, I'm not going to do this accurately, but that's pretty much what it looks like. So my domain becomes all values of x such that x has to be greater than 0 now. Okay. My range becomes all real numbers instead. Increasing is from 0 to infinity. And decreasing doesn't have it in this case. My end behavior looks something like this. As x approaches negative infinity, my f of x, I'm sorry, I did this backwards. As x is approaching 0, my f of x is approaching negative infinity. As my x is approaching positive infinity, my f of x is approaching positive infinity. Okay. That's in behavior. Okay. Log base 1/2 of x. Again, I'm going to graph it to show you here. I'm going to write as 0.5 because 1/2 and 0.5 are the same thing. This is what my graph looks like now. So again, I have a vertical asymptote of 0. My x-intercept, I believe, is still at 1, 0. Yep, there it is. Looks something like this. Okay, it's not going to be perfect, I know. My domain doesn't change. My range doesn't change. I want to write it as negative infinity for whatever reason. Increasing, it is not increasing in this case. It is definitely decreasing from 0 to infinity now. My in behavior, so as x is approaching 0, my f of x is approaching negative infinity. As my x is approaching a positive infinity, I wrote that backwards. This is a positive infinity here. Sorry. As it's going this direction, it's going up. This one's approaching negative infinity. Kind of like that. Okay. And I can do natural log the same way. This one right here, I can do it the same way. Number 5 is the one that's a little interesting. I'm going to show you what number 5 does. And then I'll stop. So this is negative log base 2. And what is that? X minus 2. Kind of like this. It looks like this now. Now, the reason I'm showing you this is because I want you to notice that this right here doesn't continue up. And it actually does, but your calculator just doesn't work like that. So what I want to show you is this right here is going to shift your asymptote to 2. I'm sorry, not y, x. That means right here at 2, you're going to have that. And that also means that your x-intercept is going to shift to 3 because I moved everything over by 2 units. So my graph looks more like this now. Again, not perfect. My domain is going to change because of that. Sorry, this is 2, not 3. My range, not so much. X-intercept is now 3, 0. Increasing, it is not. Decreasing, it is now decreasing from 3 to infinity. Dang it, not 3, it is 2 to infinity. And then my in behavior is going to change a little bit too, so that x approaches 2. My f of x is approaching infinity. Positive infinity. My f of x is approaching negative infinity. Kind of like that. Okay. So that little shift is going to do that. Okay. So you have parent logarithm properties. Okay. Again, my suggestion would be to have this because that's going to be kind of your idea in terms of what you want to do. And yeah, we'll see y'all later.